All right, we're going to dive right in. Last time I introduced you to this idea of online algorithms, where you are trying to execute an algorithm that is running continuously as input arrives and needs to respond to the input as it arrives. It can't wait for it all to be there before the algorithm makes any decisions. And our goal is to develop good algorithms, but the first step is to understand what it means to be good, right? And so I talked about this informally last time, but now we are going to formalize that. So this is online algorithms. And the model here is that the input is a sequence, sigma, which is unknown in advance. And that often includes n being unknown. You don't know how long the sequence is going to be. Your algorithm must respond with an output or an action or whatever it is that the algorithm does to each symbol. And this accumulates a cost over the whole sequence. And one place where we've seen this model is with data structures, where the sequence is a sequence of API calls to the data structure. You insert something, you search for something, you delete for something, so on and so forth. So each of those operations is one of these symbols. The data structure has to do something, right? In this case, it has to update the data structure in some way, and there's a cost for that action. So for data structures, it's the time that it takes to update the data structure, right, or to execute the query. And so we can look at the total cost of any algorithm over a particular sequence. And of course, the cost varies for different sequences. So you might think, I'll just look at the largest cost over all possible sequences, right, as a measure of the performance of the algorithm. The problem is that for some sequences, there's just no way to get a good cost. And we talked about some of those last time. So you don't want to compare to that sort of absolute worst case. Instead, you want some more appropriate gold standard to compare to. So you compare it to this optimal algorithm or this minimum algorithm that knows the sequence as it runs. So it still has to do all of the actions or operations or whatever, but it knows all of the requests, all of the symbols that are going to arrive in the future. And we say that our algorithm is k-competitive if, for any input sequence, the cost of the algorithm is at most k times the cost of the prophetic algorithm. Okay? And you'll notice that we're using a multiplicative measure of performance. And this is really for the same reason as we did with approximation algorithms, that you can, in some cases, talk about additive measures of competitiveness. But usually, by making the sequence longer, you can amplify any additive measure of performance, whereas a multiplicative measure of performance is robust to arbitrarily long sequences. Okay? This all making sense? All right. So that's our definition. Sometimes we can talk about being asymptotically k-competitive. Where we allow a kind of a startup cost. Okay, like to just get started. As your sequence gets longer and longer, of course, this additive factor becomes negligible, so we don't worry about it. Okay. So that's the formalization. Let's look at a sample problem. This is a problem of great importance in modern civilization. It's called the ski rental problem. Okay, right up there with how to reduce polarization in social media. So the idea here is that there is a sequence of days where you might go skiing. And each day, you have a choice. You can rent skis for $1, or you can buy skis for $T. Okay. And every day, when you decide to go skiing, you have to decide which of those two things to do. Obviously, if you buy skis, you never have to rent them again, right? So that seems like an appealing prospect. So how about just buying them on day one? Would that be a good strategy? Buy skis the first time you go skiing? Yeah.
Maybe you don't even like skiing.
Maybe you don't like skiing, right? So if you buy on day one, well, you might stop then, right, after you bought your skis. Okay, so you pay $T. Opt pays $1, and you have serious regret for having lost your money. This competitive rate, what is called up here a competitive ratio, is also sometimes referred to as the regret ratio. Right? Oh my God, I could have had all this money to spend on video games, and instead I blew it on skis. Okay? All right, so if buying is a bad idea, maybe we shouldn't buy. Maybe we should just rent whenever. How's that as a strategy? Is that competitive with the optimum in some way? Yeah? Exactly. If skiing becomes your life, then you're going to pay infinity dollars. Whereas Opt, which knows that skiing is going to become your life, is only going to pay $T. And so you are not competitive at all, right? Your ratio is arbitrarily bad compared to the optimum algorithm. Okay? So what should you do instead? Well, what is the range of things you could do, right? What is the space of possible algorithms for the ski rental problem? Yes?
After how many rentals you could spot.
Exactly. You can rent for some number of days and then buy. Right? And this is the entire space of algorithms, because the only input you have is how many days have you skied, and right, that's the only information you have. So it's the only thing you can use to decide what to do. Okay, so what we can consider doing is to rent for D days and then buy. Okay. Okay. And different Ds define different algorithms. So the question is, what should D be? In order to answer that, we're going to think about what is the competitive ratio for different values of D. Okay. And this is an adversarial setting, right? If once we pick an algorithm, there is some particular sequence which gives the worst case ratio between us and the optimal algorithm, right? So what is that worst case sequence going to be? Yes?
That will make go C for D plus 1 then.
Good. So it seems intuitive that the very worst thing for nature to do, right, is to end your skiing career the minute you buy skis, right? Why is that? Well, suppose that we end before. Suppose that the sequence ends before we buy the skis. Then how are we doing? Yeah. It kind of depends, actually. Actually, that may not have been a good question to ask. If it ends before we buy the skis, sorry, that's not actually a good question. Let me sort of describe it this way, right? If the sequence ends before we buy the skis, then it gets worse if it gets longer. Okay, we have to sort of consider a bunch of different cases according to what the optimum algorithm does, right? So basically, before I buy the skis, the adversary is either still renting, which would give me a ratio of 1, right, that we're both renting, right? Or possibly the adversary has bought. Okay. But then extra days only make things worse. Right? On the other hand, if it keeps going past the time when I buy, then, well, if the adversary is still renting, the ratio is getting better, right? And if the adversary has also bought, then neither of us is paying anything, so nothing is changing, right? And if the adversary bought, continuing changes nothing. So the worst case is that the day that I buy skis is the last day that I ski. Remember this. Just think about this when you're out on your ski trips. Okay? All right, so what is the ratio? Okay, so we're now looking at day D, or at day D plus 1. Right? And I pay D plus T. What does the adversary pay? Remember that the adversary knows that we are going to be skiing for exactly D plus 1 days.
D plus 1 was less than T, then D plus 1, otherwise.
Exactly. The adversary, if you think about it, since the adversary knows how many days you're going to ski, it will either buy at the beginning or not buy, right? If the adversary is going to buy, then it'll do so right away because that's the cheapest way to buy. So the adversary pays the smaller of D plus 1 and T. Right? That means that the ratio is just D plus T divided by the smaller plus 1 and t. Okay. Now, if you think about it, if d is smaller than t, then as you increase d, the denominator increases, right? So you shouldn't make d smaller than t if you're trying to minimize the ratio, right? You should grow d until d is equal to t. Right? At that point, if you keep increasing things, you're also going to be increasing the numerator, and it's going to make things worse again. So, yes? What was that?
So then you keep on going up to d plus 1.
Exactly. So that's where you stop, right? You stop where that's the optimum threshold is when d plus 1 is equal to t. Okay. And at that point, you get a two-competitive algorithm. Okay. So this is a simple rule, right, that says rent until you've spent $t and then buy. So you've spent the same on renting as you have on buying. And that means that you are within a factor of 2 of the optimum. Either you stop before you buy, in which case you're actually optimal, right? Or at worst, you pay double your rental cost, which means you're within a factor of 2 of optimum. Is this clear? Any questions? All right. Turns out this is also the best you can do. Our proof kind of shows that if you look at it more carefully. You can't really beat a factor of 2, unless you play a trick, which we're going to look at later, which is to randomize. Okay? If you introduce some randomization into your decision making so that the adversary doesn't know what you're going to do, you can actually do better than a factor of 2. And that would be on your homework, but I'm not going to get to it in time, so I left it off for this year. Okay? But I'll put it on as an optional problem for later for those of you who want to play with it. All right. For those of you who are, double with course 15, let's look at finance. Okay. So suppose that we have, what would be a good thing to have? Boba. Okay. So we have a large supply of boba. Let's say 1 unit of, oh, wait a minute. Which order do I want to do this? Yeah, let's do a car first. Okay. We want to sell a car. We have a price each day when we could sell the car or not sell the car. And our goal is to make a good, make good money off of selling the car. What should we do? Now, as stated, we can't really achieve anything useful. Okay? Any day that I sell the car, the next day the price could become infinite. Okay? So we need to refine the statement of the problem a little bit. I'm going to tell you that there's a maximum price of big M. Okay? So at least you can know if you're getting close to the maximum price. Now, the other thing that you have to worry about is that if I choose not to sell the car on the first day, then the green revolution might come and nobody might want a car anymore. And then I get 0. And so my 0 would be infinitely bad compared to the optimum. So we're also going to allow for a minimum price, M, little m, that I can get if the market closes. Or alternatively, you can say that I know the last day. I'm warned when it's my last chance to sell so that I can always sell for at least the minimum price. So we have this high value and this low value. what should we do if we want to be competitive to selling at the best possible price? And I'll again ask, what is the range of possible algorithms, right? Each day you're being told a price. So what is the class of algorithms that you might choose to execute? Yes?
Question, is number of days finite?
It is finite but not known. Except, as I said, you do get a warning on the last day so that you can sell for the minimum price. So what are your algorithms, right? You hear a price today. How do you decide, what algorithmic rule can you use to decide whether to sell? Yes?
I have a question. Does MaxM tell you that there's a day where the cost is M?
No. These are largest achievable and smallest achievable prices, but there's no guarantee that they ever occur. Yes? What was that?
It's rank.
It's rank. Okay, so you could say if I see like the highest price that I've seen so far, I should sell at that price, right? I think this one's a little problematic because I think that algorithm would pretty much always trigger on the first day, right? I guess if you say I want the third highest price, you'd have to wait for 3 days or something like that. Yeah, any other thought? Yeah?
I think in general you just need to fix a price.
Okay, so a natural set of algorithms is sort of a reserve price, right? If I see a price above P, then I will sell at the stated price. And I'll just wait until I see a price above P. Okay? So how do we analyze the competitive ratio of this algorithm? Well, what are possible outcomes if I set a reserve price of P? Yeah?
Maybe if we waited, the price went all the way up to M.
Good. So one possibility is that we sell at P, but the price rises to M. Right? So the ratio that we achieve is RP divided by that large M. Right? What else might happen? Yeah?
Price never gets to P.
What does it get to? So if the price never gets to P, that means we don't sell, right? So what would be the worst case outcome of our not selling? Yeah? Oh, that wasn't a hand.
Lowercase m.
Yeah, we sell at M. What does the adversary get to do? Yeah? Yeah, or I mean, I'm not assuming integers, but let's say the adversary sells at P minus epsilon, right? So now our ratio is the M that we get divided by that P minus epsilon. And I'll just say M over P, right? We'll make epsilon arbitrarily small. All right? So the adversary is trying to make things bad for us. So after we decide what our P is, the adversary is going to make things the worst of these two outcomes, right? So overall, our ratio is going to be the maximum of P over big M and little m over P, right? Oh, sorry, the minimum, because of the way that I wrote it. So what do we want to do? Well, we want the largest possible fraction of the achievable, right? We want a competitive ratio that's as large as possible in this case. So how do we get that? Yeah.
Square root of m, small m, big m.
Exactly. The usual thing, we balance these two terms. Right? We arrange that p over big M is equal to little m over p, which means that p is equal to the square root of big M times little m, right? Which means that our ratio is the square root of little m over big M. Okay. Which is not great, but again, is the best that you can hope to do in a ratio sense. Now, you'll note in this case, our performance is very dependent on our measure of performance, right? We've tried to optimize the ratio. You could instead design an algorithm to optimize for an additive difference. And this would use a threshold of m plus m over, big M plus little m over 2, so that you were within half, right, additive distance. But that's because we only have really one action here, so there isn't this opportunity to make the sequence infinitely long in order to amplify an additive competitive ratio. So in this special case, you might want to think about an additive competitive ratio, but in general, you wouldn't. Let's ask how things change if instead of selling a car, you're selling your supply of boba. Okay. Why should this be different? Well, because you can sell pieces, you can sell fractions. Right? You don't have to sell it all at once. You can get those tiny little cups and pour out little bits of boba for different people on different days. Okay? I guess those pearls, right, they have a minimum size, but let's not worry about that. Okay? So, is there a different algorithm for this fractional case that will outperform the car? We could use the car algorithm, but I claim that with this ability to divide our product, we can do better. Yes.
Maybe we can choose like a big threshold and a small threshold.
Good. So imagine that, I mean, over there, we kind of split the range geometrically, right, into, upper and lower halves in a geometric sense, right? And and by taking the middle, we were able to get close to the ends of the thing, right? But as you say, imagine that we split our boba into two, okay? And instead of making one center geometric threshold, we split it into thirds geometrically. So there'd be a sort of a high threshold and a low threshold. And we sold half the boba at the high threshold and half the boba at the low threshold. Okay? So divide in two. We've got the same issue with the big M and the little m, right? But we can have half reserved to price P1 equal little m to the 2/3, big M to the 1/3. And the other half reserved to price P2 equal little m to the 1/3, big M to the 2/3. And I claim that this works better, right? What's great about this? How do you analyze the performance now? So again, what's the optimum algorithm going to do? Which is also right. The adversary is both picking the optimum algorithm and picking the sequence that you're optimum algorithm is going to use. So what is the optimum algorithm going to do? Well, it's just going to sell at the best price, right? It knows the entire price history, so it will just sell at the best price. So how do we compare what we're doing to that best price sale? Yes?
We can like consider whether the best price is like below P1, like between P1 and P2.
Good. So if the best price is less than P1, which is less than P2, by the way, right? Then what happens? Yeah?
Your cube root and away from the optimal solution.
Exactly, right? So if the best price is in this range, then the adversary is actually, again, they're picking the worst case scenario. They're just going to set the best price to be P1 minus epsilon, right? Because that does satisfy the event of the price being less than P1. And in that case, we get little m, because we sell both of our batches at the last minute, okay, when boba goes out of style. And the adversary gets P1. So our ratio is m over P1, right? Which is m to the 1/3 divided by big M to the 1/3. What else might happen? We have to consider all the possible cases, right, and argue that we're competitive to all the inputs. Yeah?
It could be P2 minus epsilon.
Good. All right. If the best price is bigger than P1 but less than P2, in other words, P2 minus epsilon is what the adversary is where it is for to make things best for the adversary, right? Then what do we get? Well, we have these two different reserve prices, but since it reached P2 minus epsilon, that means we sell half our batch at P1, right? So we get half P1. Right? We also get m, little m, for the second batch that we never reached the reserve price, but that's negligible compared to P1, so we won't worry about it. Okay. But the adversary gets P2 minus epsilon, but I'll ignore that. So the ratio now is P1 over P2 times a half, right? Which is equal to 1/2 of the cube root of m over m. Case 3 is where it's bigger than P2, which means that we sell both of our batches. The P1 batch is negligible, but we still get to sell half of our stuff at P2, right? And so again, the ratio now becomes 1/2 of P2 divided by big M, which is again 1/2 of the cube root of m over m. So basically, instead of the square root of m over m, we're going with the cube root of m over m, which is an improvement. Okay. So, any questions? Yes? Yeah. This is a natural question. Does this generalize, right? Here we made 2 thresholds, but we could instead make 3 thresholds or 4 thresholds. Right? So if you play around with that a little bit, and you realize that constant factors don't matter, what with us being theoreticians and all, what it makes sense to do is to break things into powers of 2. So your reserve prices are 2m, 4m, 8m, and so so forth, up to m over 2 and m. Here I'm assuming big M is a power of 2 times little m, right? So how many of these different reserve prices are there? Yeah.
Small, big M.
Good. Okay, and so we're just going to evenly divide up our boba into these log m over m glasses, right? And each glass will be at a different reserve price. Okay. And right, the optimum price, the max price, will be between some 2 to the I times little m and 2 to the I plus 1 times little m for some I, right? And that means that we will sell a 1 over log m over m fraction of our total at price 2 to the I times little m. Whereas the adversary, knowing the future, will sell all at the highest possible price, which in the worst case is 2 to the I plus 1 times little m. So our ratio is 1 over log m over m times 2 to the I, all divided by 2 to the I plus 1, which is 1 over 2 log big M over little m. So in fact, the ability to subdivide our commodity, right, lets us improve from a square root competitive ratio to a log competitive ratio of the ratio between the max and min prices. Okay, pretty dramatic improvement. Yes?
Why are we selling 1 over log m over m fraction?
Because we have to keep some of our commodity for each possible reserve price. So yes, so you're right. So in fact, actually, I can be a little more precise here, right? If we're selling if the price gets up to something between 2 to the I m and 2 to the I plus 1 m, then we're going to be selling at threshold 2 to the I, but also at threshold 2 to the I minus 1, and threshold 2 to the I minus 2, and threshold 2 to the I minus 3, and so forth, right? So in fact, we're going to be getting this. Yes? All of those smaller thresholds. And that takes care of this factor of 2, right? Here we have this sums up to 2 to the I plus 1 with a little fudge. Yes? All right, so subdivision, very powerful. Let's go back to the car for a second. We can't really sell the car in pieces, right? Nobody wants just the tires. Well, maybe they do. But we can use randomization to have the same effect. Anybody see how? Yeah?
Like the probability you sell a car at a certain price has to do with like the fraction on it.
Exactly. We can use coin flips to decide whether to sell as we see various prices. Right? Actually, I'm not going to spend a lot of time on this, but imagine that among these different reserve prices, we pick one of them at random. Okay? So we pick one of these reserve prices at random. There is a 1 over log chance that we pick the right one, which is within a factor of 2 of the max price. Yes? So with 1 over log m over m probability, we are going to sell within half of the max price. So in expectation, we are going to earn a 1 over log m over m fraction of the max price. So that's just a cute little example of how you can use randomization. It's kind of like randomized rounding, but backwards, right? We're using randomization to, oh, sorry, it is randomized rounding. We're using randomization to take a fractional strategy and turn it into an integral strategy. All right? Any questions? Okay, so ski rental, stock market, these were sort of relatively elementary problem formulations with easy solutions. Let's start to get a little bit fancier. Let's go back to scheduling theory. Scheduling theory is a great place to think about online algorithms, right? There are many situations in which your work arrives over time, but you need to do it when it arrives. You can't wait until all, I mean, if you wait until all of the work has arrived, you've just wasted a ton of time that you could have spent doing work, right? So a simple canonical example of this kind of online problem is, right, you've got your M machines, jobs arrive, you have to assign every job to a machine at the moment of arrival. And at the end of the day, they ask you, you know, how high did the load go on your most loaded machine? Okay. So what would be a good online algorithm that would give you a good competitive ratio against, for this kind of scheduling problem? And again, what's weird here is you never know when the job is, when the problem is over, right? Jobs arrive, some unknown number of jobs is going to arrive, and at any moment, your boss could walk in and say, okay, now is the moment I want to check the load on the machines, and it has to be good compared to the optimum. So what should I do? I will give a hint, you don't have to develop any new algorithms. Yeah.
We still just assign it to the one with the lowest.
Yeah. Graham's rule is an online algorithm. Right? It schedules jobs as they come in to put each one on the least loaded machine. And we showed that it's a 2 approximation. Right? And it's a 2 approximation to an unknown optimum. But it doesn't matter that the optimum is unknown. We know we were in a factor of 2 of it. Right? And that means that we're too competitive, even though we can't figure out what the optimum is in polynomial time. Now, the refinements that we saw, right? Longest processing time first, the whole geometric, this whole sort of rounding and grouping and so on and so forth, all of those require that you have all of the jobs in hand before you do the schedule, so they're not online, right? So that means that there's now a question, is, you know, we know that Graham's rule is not the best approximation algorithm, but is it the best online algorithm? Is there something better to do than just always putting every job on the least loaded machine? Yeah?
Can we pause a job and then continue?
So this formulation, right, PC max does not include a preemption option, right? And preemption by itself doesn't really mean anything if you're just looking at maximum load. You would also have to think about migrating the job to another machine. And so there are versions of scheduling where you're allowed to pause and migrate a job at some cost, but that's not the one that we're looking at right now. Okay. So for a really long time, nobody was able to come up with anything better than Graham's algorithm. And Graham's algorithm is from the 60s, if I remember correctly. Okay. But in 1995, Bartal, Fiat, some other people managed to beat Graham's algorithm. Okay. They gave an online algorithm with a competitive ratio of 2 minus 1/70th. Okay. And so there's two ways to look at this, right? One way to look at this is, what's the big deal? 1/70th. Right? The other way to look at it is, this stood for 35 years, and finally somebody was able to find an improvement. Right? And they did it with actually a pretty nice insight, forgetting for a moment about the improvement in performance, right? By thinking about what goes wrong with Graham's algorithm. Why does Graham's algorithm end up with a factor of 2 competitive ratio? What is the bad input that makes Graham's algorithm do much worse than optimum? Anybody remember? We talked about it in the approximation setting. Yeah?
I think it's like the biggest load is at the end.
Yeah. If you send a huge number of tiny jobs in, Graham's algorithm will evenly schedule all of the machines. Then you send in a job that's as big as the current load of all the machines. And so that job comes in and doubles the load of one of the machines. And now is when you have your moment of regret, right? What should you have done? Yes? Yes. And in particular, for that example, if you'd left one machine empty, right, it wouldn't have meant a lot more load on any of the machines if you left one machine empty. And then you would have a free machine to take this highly loaded job that arrives at the end. Okay? And so Bartal and Fiat figured out how to generalize this observation. Their idea is to have 2 classes. The problem is if you imagine that you just kept one machine empty, what would the adversary do? Yeah?
It would like just make it so you needed 2 machines empty? Like
Exactly. It would send you a giant job, and then and then it would send you another giant job. Right? And now that job would, and so you think, oh gosh, I should have left 2 machines empty. Right? But if you leave 2 empty, then he'll send 3. Right? So they had to sort of think about this in general. They had 2 categories of machines. Okay. The light ones were just slightly less loaded by about a 1/70th factor than the heavy ones. Okay. And small jobs would go on the heavy machines as much as possible. But if you got a big job, a huge job, would go onto a light machine. Now, putting a huge job on a light machine makes it heavy, but the arrival of this extra work also changes the threshold of what it means to be light or heavy. And that's where the 1/70th comes from, is that it's just sort of, it balances these things properly, so that even if you put big jobs onto the light machines, you're still left with enough light machines to capture later big jobs, because the notion of light keeps evolving as more work arrives. Okay? So does the intuition, I mean, the math is hairy, but does the intuition make sense? All right. So this actually came out when I was in graduate school, and we were like, we ask the obvious question again. Does this generalize, right? What if you make 3 groups of machines, light, medium, and heavy, right? And the math was too hairy for us to do, so we gave it to a computer, okay? We actually, a bunch of us graduate students, we basically wrote a linear program whose optimum explained how to divide up the work into different heavy and light categories. This is 1.986. Our massive linear program, which took several days to run, improved this by the massive amount of 0.04, right? Okay. And then somebody else, this was in 96, and then Albers in 97. She was smarter than us. She didn't need to use a computer. She just did something theoretical and got it down to 1.923. And since then, I haven't really paid attention, but I'm sure that the numbers have gone down and down. But I also, as far as I know, they do not yet have the final number, right? There's some limit to this. Right? You can't be one competitive. So somewhere is the best possible competitive ratio for this problem. And it's not there yet. So, I mean, again, your projects are due soon. Your project proposals are due soon. So this would be something that you could work on. Okay? So, and so this is just one example of an online scheduling problem. But in scheduling theory, online scheduling is almost as large a domain as offline scheduling. And again, pretty much any problem has an online version that you can look at. Any questions? Okay. Yes?
Can you do the with a randomized algorithm?
That's a good question. I am not familiar with papers on this particular problem where randomization has helped. But that doesn't mean it can't. All right. Let's take our 2-minute break. Wall sits are good, but they're not aerobic. You need you want to get the blood flowing for math class, right? All right, let's resume. You're welcome to stay seated at the wall for now. I wanted to mention the last problem set, and this is the last problem set, by the way, the one that's due on Wednesday. It includes a project proposal, which is due next Wednesday with the rest of the PSET. With the submission instructions are there. And it pointed you at the project description on the website, but I just wanted to check if there are any questions regarding the project. No? We do want these projects to be collaborations, and so you should use the collaborator search. If you don't have a collaborator yet, track one down using that collaborator search approach that we asked for. Yeah, so the last problem set is due Wednesday because after Thanksgiving, I want you to be able to concentrate on your projects. I can and usually do give some optional lectures of just more algorithms because there's always more algorithms and they're fun. And I will do that on Mondays and Wednesdays, but not Fridays for as long as people keep coming. You can vote with your feet about when things get too stressful at the end of the semester and you just don't want to bother anymore. And I may hand out some optional problems for those of you who just want more work. And we'll arrange to get those graded. Okay? So any questions? Oh, I had one other question, which is whether we should have lecture on Wednesday, the day before Thanksgiving. How many people are going to be around and inclined to attend a lecture? Really? We don't have everybody going home for? Wow. Okay, I'm touched. All right. Well, if there's so many people here, I will lecture. But of course, since the problem set is due that day, I can't really ask you any questions about that day's material. So that will sort of be our first optional lecture. Right? Because it's the last problem set, I kind of stretched a little bit. So I think one of the problems may rely on something that I tell you on Monday, but certainly it won't rely on anything that I tell you on Wednesday, since it'll already be in at that point. Okay? So now that we've gotten through these preliminaries, these more basic algorithms, I want to show you the problem for which competitive analysis was actually created, which was the paging problem. So the idea behind paging is that you have a computer with a fast internal memory of k blocks. And it also has external storage of infinite size. But this is slow. So the fast internal memory, the cost of accessing anything in it is effectively 0. However, anytime you have to access a block in external memory, that has a cost of 1. Okay. And when you access something in external storage, you do that by bringing it into internal memory. So you fetch a block of the external storage into the internal memory. Okay. But the external storage is very big, so you have to evict some internal block to external storage. make room for what you want to bring in. And so this poses an obvious question of what to evict. And you know, these requests, these accesses to memory, of course, being driven by some program that's running in the computer, but we don't actually care what the program is doing. All that matters to us is the sequence of memory requests, okay? And how we respond to that sequence of memory requests. The cost of our algorithm is the number of what are called misses, which is when the memory that you want, or the block that you want, is in external storage and has to be brought in. Okay. So is the problem formulation clear? All right. So any thoughts on what might be a good strategy for deciding what to evict? I don't know. I mean, I think, do you do virtual memory in 004? I don't remember. So you've probably seen some eviction strategies. What would be some options? Yeah? Good. So one that's very popular is known as LRU, least recently used. Which does what it says. Every time you have a miss, you evict the internal block, the in-memory block, that was the least recently used of all of the internal memory blocks. Okay. What are some other strategies that you might consider? Yeah? Most recently used, right? What would be the intuitions behind these? Exactly. That if you're sort of looping over memory many, many times, then the most recent block is actually the one that is going to be the longest before you use it again. Right? What's the rationale for least recently used? Yeah?
You used it like one time and you stopped using it.
Yeah, this is sort of the locality of reference argument, that like once you're paying attention to something, you're going to keep doing it for a while, so you should keep it around in memory because you're likely to hit it again. Okay. There are some other variants which in a sense are just kind of simplified versions of these. So FIFO, right? When you have a miss, you just you evict the oldest block that you brought in, whether you used it or not. So that kind of corresponds to LRU. There's also LIFO, last in, first out, which is essentially which is equivalent to the most recently used procedure, right? There's an even more simplistic one called flush when full, which basically says whenever you fill up with memory, you just dump it all out, and now you're empty and you can fetch k new things. Okay, so there are quite a wide range of options. Okay? And again, if you want to understand which of these is a good option and which of them is a bad option, you have to think about how you're measuring good versus bad. Right? If you just said an algorithm is good if it has few misses, then that actually wouldn't allow you to distinguish between these algorithms. Right? How come? Why is just measuring the worst case number of misses not a useful way to assess a paging algorithm? Yes?
So that you care about the expected number, not the worst case?
Oh, actually, we do care about the worst case. Competitive analysis is all about the worst case. It's about the worst case input sequence, but it's not. But in competitive analysis, we say relative to the best possible algorithm. Why do we make that qualification? Why don't we just talk about the worst possible outcome? Yes? Yeah, what would be the worst case for a paging algorithm? And what might cause that to happen? What kind of request sequence would force you to get something from external memory every single time? So yes, although that's an adaptive sequence, right, where you don't actually need that in this case. You can make an unadaptive sequence that's arbitrarily bad. Yeah?
Take unique numbers, unique accesses.
Yeah. If you just keep accessing new things over and over again, there are always going to be misses, right? And since the external memory is infinite, you'll never run out of new things to access. So under that measure, there's just no difference. But it's not interesting, right? We know that that's just a ridiculous sequence that no algorithm can do well on, so we kind of want to exclude it from consideration. And so what we really want to say is, which of these algorithms does well when it's possible to do well? Okay? And for that, it actually turns out that there are differences. So what we are going to show is that FIFO and LRU and flush when full are K competitive. K is that number of blocks that we have. Okay. MRU and LIFO are not competitive at all. They can be arbitrarily bad compared to the optimum. Okay. Yes?
Is that additive competitive or multiplicative?
Multiplicative. Okay, so yes, that's a pretty bad, I mean, you know, we're talking about right, so in a modern machine, K is, you know, maybe 1,000. If you talk about the block, or could be 1,000,000, depending, right? So it's a pretty large constant, but it's a constant. Now, there are actually refinements of the analysis that I'm going to give you, which give you more optimistic numbers that mean something, but we'll get to that. Okay? For now, let's just prove that there is a difference, that you can actually be constant factor competitive. Okay? So let me start with an easy analysis. Okay? For the easy analysis, I'm just going to prove that we're K+1 competitive. Okay. So what I'm going to do is I'm going to consider my request sequence sigma. And I'm going to break it into maximal phases of K+1 faults by my algorithm. So let's look at LRU. I'm going to show you the analysis for LRU. You can go back and do it for FIFO if you want to. Okay, so we consider any sequence, and we look at what LRU does. And on every K+1 fault, we declare the end of a phase, and we start looking at a new phase. Okay? So if there are K+1 distinct faults, what can we say about this phase? Well, I claim that if there are only K pages requested, then you won't have K+1 faults. Why is that? So suppose that there are only K distinct pages requested during this phase, right? What can you say about those pages and the faults? Yeah?
We never even.
Right. If there are only K pages requested, none are evicted, which means that we have at most one fault per page. Right? So if there are only K pages in the phase, then there are at most K faults, and so the phase has K+1 faults, so there have to be more than k pages requested. Now, if more than k pages are requested in a phase, what can we say about opt? Yeah? Right. K+1 requests, well, they can't all fit in memory. So that means that opt, whatever the optimum algorithm is, it must miss at least once. And so we're done, right? Every time we see k+1 faults of LRU, we can associate that with one fault that happens in that phase during opt. Okay? And so we have our k+1 competitive analysis. Okay? Now, if we refine that analysis a little bit, we can actually improve the competitive ratio to k. All right? I'm not sure I can give you all of the details, but let's get started. I'm going to break it not into phases of k+1 faults, but into phases of k faults. This is sort of the natural thing to do if I want to prove a k competitive ratio. I want to basically say that for every k faults by my algorithm, opt faults once. But you see the problem here. It's like if there's only k faults, maybe somehow opt managed to get all of those k pages into memory and doesn't fault on any of them. So how do we get the one fault for opt when we're looking at k faults by notice that a phase begins with a fault. Right? It basically begins with the k plus first fault, because that's the first request that can't fit into the previous phase. Okay. And let's let Q be the last page requested before some current phase. We basically have to do some more careful analysis to find a page to blame opt for, to make opt fault on. Okay, and that's what we're going to do. Now notice that Q is initially in memory. Okay, and so that's going to become our source of blame, because there's this page that's in memory that's not actually part of this phase. It's a page that was requested in the previous phase. Okay, so case one is that our algorithm, LRU, faults on Q in this phase. Okay. Why would LRU fault on Q? Well, Q is the least recently used at the beginning of the phase, because we just asked for it. So the only way to make a fault happen is to evict Q. And in order to evict Q, you have to get k other pages to be more recent than Q. So you're going to need k distinct requests in this phase that are not Q. Okay? So there are k requests other than Q in this phase. Okay? So that means that we have k requests here along with the request for Q that happened in the previous phase. So that's k plus 1 distinct pages, which means that opt faults on one of them. Okay. But it faults during this phase. It doesn't fault during the request for Q. And we're finding a fault that happens in this phase by opt. Case two is that LRU faults on a different page. But it does so twice. Okay. And again, for that to happen, there must be k other requests between those two faults. So k plus 1 in total. So opt must fault on one of those as well. Case 3 is that there is no fault on Q or twice on any page. And that means that Q is in the cache at the start and stays there. It's never evicted. Okay. Which means that the k faults that happen in the phase must be for other pages. And that again gives us k plus 1 distinct requests in total. So we can conclude also in this case that opt must fault. Okay. I'm rushing a little because we're out of time, but these are the 3 cases. We've shown that in each of these 3 cases, even though we're only looking at k faults in a phase, in any one of the cases, opt has at least 1 fault during the phase. So for every k faults by LRU, there is at least 1 fault by opt, and that makes opt k competitive. Now, what's the big deal about k versus k plus 1? Well, the big deal is that we can actually show that k is the best possible result. That no algorithm is better than k competitive. Okay. And we do that by designing an adversary that that generates a sequence. So we're given our algorithm, and we're going to generate a sequence with a bad ratio. And it's actually pretty easy to do. We're only going to use k plus 1 pages, k plus 1 distinct pages that we ask for. And the adversarial sequence is that each request is for the page our algorithm doesn't have. So if every request is for the page our algorithm doesn't have, the algorithm faults every step. Right? Well, we know that it's easy to make request sequences where the algorithm faults every step. But what's interesting about this sequence is that we can have a prophetic algorithm that does well on this sequence. Okay? So what is the prophetic algorithm doing? Okay? It gets a request sequence. I mean, initially it's empty, it's going to have faults, but its cache is going to get populated. And the question is, what should the prophetic algorithm do when it sees a fault? How can it avoid making a lot of faults going forward? What should we evict? Yes?
You can use MRU,
What do you mean?
like the most recent, instead of this recent.
Well, if I evict the most recently used page, it's possible that the sequence might ask for it again. Right? I mean, if a page is asked for twice in a row, then, or 3 times in a row, then right, you could get into trouble. Okay? But I'm going to play a nasty trick, right? I know the sequence, so I'm going to evict the page that is not requested in the next k requests. Okay, right? I made the bad sequence before I designed the optimum algorithm. Okay, so I look at this sequence, and I build my algorithm based on the sequence. When there's a fault, when I don't have the page, I look at the next k requests, right? And I look at the next k plus 1 requests, right? And I evict the page that is not asked for in the next k steps. And that means that my algorithm only faults every k steps. And so I've just shown that my algorithm is not doing, that the proposed algorithm cannot do better than a factor of k, because there's at least one sequence on which it is off by a factor of k. So the factor of k bound that we gave on the other board is tight. You can't beat k competitive, and LRU and FIFO are k competitive. Okay? So I'll leave you with 2 things here. One is that, as I said, k competitive is a very disappointing number. If you generalize your ideas and talk about something called resource augmentation, so we know that the online algorithm is less powerful than the prophetic algorithm, so let's give it more space. So let's give the online algorithm some amount h larger than k space versus the optimum algorithm, which only has k space. It turns out that if you do that, if you take a little extra space, then LRU is k over k minus h plus 1 competitive. You can generalize the proof that I gave over there. So in particular, sorry, did I do that backwards? Yeah. It's h over h minus k plus 1 competitive, because h is bigger than k. So we showed that when h is equal to k, you're just h competitive. But if, for example, you give your online algorithm twice as much space, then you end up with a 2 competitive algorithm. So essentially, this online algorithm is 2 competitive against an offline algorithm with half as much space. And that's a reasonable, it's sort of a reasonable thing to say, that you're trading a little extra space for the ability to see the future. Okay? Now, looking ahead to Monday, if we look at this bad case, this relied on the adversary looking very carefully at what our algorithm did in order to design a worst case outcome for our algorithm. Right? If you think about this, an analog would be, you know, if you're playing poker, you get to look at your opponent's cards before you make your bid. Right? So the adversary has too much information. And if we want to overcome this, we have to hide things from the adversary. And on Monday, I'm going to show you how we can do this with randomization. If we make the behavior of our algorithm unpredictable, then it becomes impossible for the adversary to design these kinds of bad sequences, and we will be able to prove a significantly better competitive ratio. Okay? So that's what we'll do on Monday, is look at randomized competitive algorithms. See you then.